We receive energy from the sun in two main forms, heat and light. Heat is used by solar thermal systems to warm up water. Solar electric systems convert light energy into electricity using photovoltaic cells. Cells are made from layers of semiconducting material, usually silicon. The conversion of light into electricity is based on three important principles. The first is excitation of free mobile charge carriers due to light absorption. The second is separation of the charge carriers, and the third one is collection of the charge carriers at the contacts. We call photovoltaic process this conversion of light into electricity. Assembly of cells are used to make up solar panels, also called solar modules. Modules or panels together constitute what we call photovoltaic arrays. Solar PV systems can be connected to the grid or can work as isolated systems for the use of a single household or institution in area where the grid is unavailable or just not reliable. Solar PV systems are on-grid when they are connected to the grid and off-grid when they are not. On-grid or grid-tied PV systems export excess energy to the grid. In case the sun is not available, the connected loads get power from the grid. An off-grid or standalone PV system involves the use of storage batteries. The batteries store the excess energy generated by the PV array, and in its turn, it provides electricity to the connected load when the sun is not available. Photovoltaic cells are categorized based on the type of semiconductor material used to build them. The three main types of PV cells in use are monocrystalline silicon, polycrystalline silicon, and thin film. The most dominant PV technology is based on the use of silicon wafers that are typically 150 to 200 microns, 1/5 of a millimeter thick. This technology represents around 90% of the current PV market and belongs to the first generation PV technology. Another PV technology based on silicon is thin film. In this case, no silicon wafers are used, but very thin layers of silicons which are deposited on glass or flexible substrate. This technology belongs to the second generation. Third generation PV technology covers a wide range of new, novel and innovative ideas. Most of them are still under testing. Apart from their visual aspect, the most obvious difference between PV cell technologies is in its conversion efficiency. Remember, solar PV modules are made of the aggregation of cells. You must now be aware that cells efficiency will impact on the size of the module. Let's explain it with an example. Under standard test condition, with an efficiency of 12.5%, a monocrystalline panel sizing 1 square meter will produce 125 watts. Under the same conditions, an amorphous silicon panel of the same size but having 5% efficiency will generate only 50 watts. Another important differentiator in solar PV performance, especially in hot climate, is the temperature coefficient of power. PV cells performance decline as cells temperature rise. Compared to crystalline technologies, thin film technologies have a lower negative temperature coefficient. In other words, they tend to lose less power of their rated capacity as temperature rises. It is important to understand the relationship between temperature and voltage. While temperature does have a slight impact on current, it has a large impact on voltage. Now, what are the PV term you should know for design purpose? You need to understand the information delivered on the module's specification sheet. You will find there the maximum power a solar module can produce, Pmax, the voltage at which maximum power is produced, Vpmax, the current at which maximum power is produced, I Pmax, the maximum possible voltage across the solar module when current is 0, VOC, the maximum possible current flowing through the solar panel when no load is connected and voltage is 0, ISC. Module performance is tested under predetermined conditions. These are the standard test conditions. To meet the test conditions, cells note ambient temperature of 25 degrees Celsius and an irradiance of 1000 watts per square meter must be respected. Now, let's come in real world conditions. In real world conditions, PV modules, I would like to say, are connected together in series making PV strings, and strings are connected together forming PV arrays. Particular attention should be given to the cables used for the connections. They must withstand environmental conditions.